Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over problems 11 to 15 of the Florida Algebra 1 Standards Assessment tests. All right, let's take a look at question 11. It says the graph shows T, the temperature of water in degrees Celsius in a test tube after n minutes of an experiment. Drag a label to each box to correctly identify the type of rate of change between temperature and time on each part of the graph. Okay, so one thing you want to keep in mind for this problem is that, one thing you want to note is that the rate of change is the same thing as what? The rate of change that's mentioned here, because I'm basically describing the rate of change of temperature over a time period. So the rate of change is the same thing as the slope. Okay, and what is your slope? Your slope is rise over run. Okay, now what do we know about slope of straight lines? Slope of straight lines is always a constant. Okay, so slopes of straight lines are always constants. They never change. So whatever set of points you pick on the straight line and you calculate the rate of change of the slope, you're going to get exactly the same number on the straight line. Okay, so if you look at this graph that we have here, we have 1, 2, 3, 4, 5 intervals, and on each interval we have a straight line. So guess what? For each interval, our slope is going to be constant. Okay, but there's a special situation for constant slopes. That is a case where the line is horizontal. Okay, so when the line is horizontal, you're going to have a special slope, which is 0 because you have no rise. So for this graph right here, this line here is constant. You're going to have a constant slope because it's a straight line. Over here, you're going to have a constant slope, but since it's horizontal, it's going to be a 0 slope. Is 0 a constant? Absolutely. Okay. And then over here, you're also going to have a constant slope. It's non-zero. It's going to be positive since it's going up. Or in this interval, you're going to have a constant slope, but since it's horizontal, what type of constant will it be? It's going to be 0. And then over here, you have a constant slope. And this one is going to be positive since it's increasing. Okay, so you have a positive slope here. You have a 0 slope here, which is also constant, positive here. A 0 slope here, which is also constant, and over here you have a positive because you're going up from left to right. Okay, so we can clearly see what our answers are for problem 11. So we just drag and drop. 0 slope goes right here, and you have a constant slope right here. Okay. All right, let's take a look at question 12. It says the production cost C in thousands of dollars for a toy company to manufacture a ball is given by the model C of x equals 75 plus 21x minus 0.72x squared, where x is the number of balls produced in 1 day in thousands. The company wants to keep its production costs at or below $125,000. The graph shows the model of the situation, so we have the graph of the situation right here. Question, what is a reasonable constraint for the model? So here we're looking at constraints on the x's. They're basically asking you for what is the domain for the feasible region given the conditions stated in this problem. Okay, so let's see what are the conditions, the constraints in x. So in order to figure this out, we have to look at what x stands for. X stands for the number of balls produced in 1 day. Okay, so is it possible to produce a negative number of balls? The answer is 0. Is no, it's impossible to create or to manufacture a negative number of balls. Okay, so that tells us that x has to be greater than or equal to 0 since it is impossible to manufacture a negative number of balls, okay, a negative number of balls. All right, so graphically, what on earth does that mean, that x is greater than 0? Well, it tells us that we are going to focus our attention to the right side of the y-axis. This is our feasible region right here, okay? Remember, our focus is on the constraints on the x-axis, okay? So if we are focusing on the right side of the x-axis, that means this side right here has to be eliminated. It's not part of our feasible region. Okay, so now we're now restricted to anywhere from here all the way to infinity. What is another constraint on the function that we're looking at in this problem? What's another constraint? Let's take a look at it. The production cost has to be at or below 125,000. So what does that mean on the graph? It means that you have to only consider the region below this horizontal line right here, okay? So you're looking downwards. All right? So what does that mean? It means that any ordered pair that's above this line has to be eliminated also. So we eliminate all this right here. Take all that out. Okay, and then we're going to have to project our remaining region on the x-axis. All right, so now let's take a look at, we have this interval right here, and then this interval, and then this interval right here. We have 3 intervals. So let's call this 1, 2, and 3. Now let's take a look at interval 3. Does it make any sense? Does it make sense for your costs to be negative? Basically, you go shopping, and you end up with money in your pockets. Does that make any sense? The answer is no. Okay, so cost cannot be negative when you're producing any kind of product. You always have to put money out of your pocket. So that tells us that x. Okay, let's also take a look at this. Well, let me state that one first. X has to be less than or equal to 32.38 since the cost C of x cannot be negative. Okay, cannot be negative. That basically restricts us to the first quadrant. Now, because of this constraint up here, we're left with only 2 intervals. Okay, interval 1, this region right here, and interval 2, this region right here. So what we're going to do is project those 2 intervals to our x-axis and read off what they are, write it in inequality notation, and that will be our final answer. Okay, so this one goes to 0 right here, and that goes down here to the x coordinate 2.62. So let's go ahead and write those down and out. So we have 0 is the lower bound, and then 2.62 is the upper bound. So this is the first constraint, reasonable constraint for a model. All right, and then the next interval that works, we have to skip this entire middle section because the cost is too much. They're not willing to pay anything more than 225,000. So ignore all that, and then the next interval that's feasible is from here to here, this interval right here. Look at the x coordinates, 26.55 for the lower bound, and then the upper bound is right here, 32.38. Okay, so constraint is going to be from 0 less than or equal to x less than or equal to 2.62 and 26.55 less than or equal to x less than or equal to 32.38. That's option letter D. All right, so we just simply check our answer right here and advance to the next question. All right, let's take a look at question 13. It says Kim is driving from Miami to Key West. The graph shows her distance from Key West. During what interval is Kim driving the fastest? Drag numbers to the boxes to complete the inequality. Okay, so what we're looking at here is speed, okay, or rate of change. Okay, so we're looking at the rate of change here. So one thing you want to note is as follows. We're looking at fastest. On what interval is Kim driving the fastest? So what does fastest mean in the context of this problem? Okay, what does the word fastest mean? Well, fastest basically means when the speed is greatest. Okay, fastest is basically when speed is what? Speed is greatest. So what this problem is asking you is, on what interval is the speed the greatest? Now in the context of a distance time graph, the speed is basically the absolute value of the rate of change or the absolute value of the slope of the line on that interval. So what we're basically looking at is the slope of the line, the linear components of this graph, distance time graph. Now if you look at it, you notice that there are 1, 2, 3, 4, 4 sections, okay? So we have interval 1 from 0 to 0.5, interval 2 from 0.5 to 2, interval 3 from 2 to 2.5, and interval 4 from 2.5 to 4. So we're going to calculate the absolute value of the slopes in all 4 intervals. And the one with the biggest value, that will be where the car is moving the fastest. We're not considering negativity here because we're looking at the distance from Miami. Okay, not distance to Key West. If we're looking at distance to Key West, then it will be this will be going upwards. Okay. Okay, so let's go ahead and take a look at them. So for interval 1, well, let's write down the formula first before we start calculating the rate of change or the slope. So the formula that we're going to be using is a rate of change which is equal to the slope is what? Rise over run. So we're going to be using our slope triangles for our calculations here. Interval number 1 from 0 to from 0 to 0.5, our slope, m, or rate of change, or the speed, we're looking at the absolute value too, is the rise over run, right? So if we draw ourselves a nice little growth triangle right here, so that's your rise, and that's your run. So we're looking at 160 minus 140, that's 20, that's your rise, divided by a run, it's negative 20, and then 0.5 minus 0 is just 0.5. Okay, so you have 0.5 here, and you have 20 over there. So that's your slope, negative 20. Or we're looking at the absolute value. Okay, so you can just plug this into your calculator. If you plug this into your calculator, you end up with positive 40 as your slope. Okay, so for interval 1, the speed is 40 miles per hour. Okay, interval 2, what do we have? For interval 2, we're going from here, going down, all the way to there. Okay, so what's the slope? Our rise is from 40 to 140, that's negative 100. Just subtract, okay, that's your delta y. And then our run is 1.5, that's your run. So for interval 2, That's from 0.5 all the way to 2. The absolute value of our slope, which is the speed, is rise, negative 100 over run, 1.5. Okay, so we can do that with a calculator. Forget about the minus, okay, because when you take the absolute value, that drops off. 100 divided by 1.5 is 66.6 repeating. So 66.6 repeating miles per hour. Now, does this make sense if you take a look at it? It should, because this line is steeper than that line. So the speed here should be greater than the speed here. Okay? And guess what? If you look at the other intervals, none of them is as steep as this. So you can automatically conclude that this has the greatest speed. But let's just do the rest. Okay? So I make sure you understand what's going on here and how to calculate slope and rate of change. So for interval 3, we are going from 2 to 2.5. Okay, so the rate of change there, the speed, or the absolute value of the slope, is rise. We don't have any rise here. Over run, 2.5 minus 2 is 0.5. So what is 0 divided by any non-zero number? 0 divided by any non-zero number is simply 0, right? So 0 divided by 0.5 is 0 miles per hour. So what on earth does this mean? It means that it looks like Kim is taking a lunch break or something like that, okay? Or refueling her tank. She is not moving. Okay, when you're not moving, then your speedometer reads 0 miles per hour. So 30 minutes break, and then she continues with her trip. Interval 4, what? Okay, let's write down what the slope is here. Slope is 0. Interval 4, what's our rise and what's our run? So for this one, our rise is going from 40 to 0. So 0 minus 40, negative 40, that's your rise. And your run is from 2.5 to 4. So it's 4 minus 2.5, which is 1.5. So that's your run, okay? Slope is rise over run. So for interval 4, which is from where to where? 2.5 to 4. The slope is, and the absolute value of the slope or the speed, or the absolute value of the rate of change is rise, which is negative 40, divided by run, 1.5, over the run, 1.5. That will give us what the speed is on that interval. Let's do that with our calculators. So what is 40? Forget about the minus because you're taking the absolute value, divided by 1.5. 26.6 repeating, so it's 26.6 repeating miles per hour. Okay, so you can see what's going on here. The fastest speed was from 0.5 to 2. Maybe she was on the freeway, all right, and then stopped, and then maybe she was on the city here. Okay, so fastest, second, third, and then last. So our answer is interval number 2 from 0.5 all the way to 2. That's when she was traveling the fastest or when she has the highest speed. Okay, so for this one, we're just going to drag and drop. The lower bound is 0.5, so you grab 0.5 and place it here. And the upper bound is 2, you drag 2 and place it here. So that's basically how you answer this question. Okay, let's take a look at question 14. It says the points on the graph show the population data in millions of the state of Florida for each decade from 1900 to 2000. The data are modeled by the function p of x equals 506,975 times 1.43 raised to the x shown on the graph. Question: what is the domain of the graph of p of x that is shown? Okay, in order for us to answer this question, we need to remember what the meaning of the word domain is. What is the meaning of the domain of the graph of a function? We have to remember that the domain of the graph of a function is the horizontal span of the graph. How wide is the graph? How far does it go to the left and how far does it go to the right? Another way to view it is the projection of the graph on the x-axis. So if you look at this graph right here, it goes from here to here. What is the horizontal span? How wide is this graph? That's what your domain is. Okay. Using the idea of projection on the x-axis, think about taking a flashlight. Okay. You take a flashlight and you flash it on this function right here. So there goes your flashlight. What kind of shadow will this graph cast on the x-axis? That is the projection of the graph on the x-axis. So if you flash your flashlight on the entire function, it's above the x-axis, so we just flash it from above. If it were beneath, we'll do up and down, just depending on the orientation of the graph. The shadow is going to look just like this. It's going to go, let me make it green. It's going to go from 0 all the way to 10. Okay, that's what your shadow is going to look like. That's what the projection of the graph onto the x-axis looks like. Now, why are we projecting it onto the x? Because the domain goes with the independent variable. Okay, domain goes with the x, and guess what goes with the y? The range. Okay, so anytime you hear domain, think about the x-axis, and if you hear range, then you think about the y. Okay, if we're doing range, we will be projecting this graph in this direction. So since we're projecting downwards, the width goes from 0 to 10. So that's what our domain is. So our domain, how wide the graph is, or the projection on the x-axis, is 0 less than or equal to x less than or equal to 10. Option letter D. All right, so we just go ahead and bubble in our correct answer and advance to the next. Okay, let's go ahead and take a look at question number 15. The last in this review installment. It says the table shows the company's income and expenses over the last 7 days. The company found that its weekly income and expenses were approximately the same from week to week. Part A, select the correct definition of the variable x. So in this problem, we're going from week to week, okay? So x basically represents the number of weeks that you're counting, all right? So if you look at the options right here, since we're going from week to week, the answer is going to be this one right here for the number of weeks. Now for the B part, the solution, this is a very involved problem, so we're gonna skip this one for this presentation. But the solution, if you want to investigate how to solve it, is 3,200 plus 10,000 equals 4,500 x. Okay, so we're not going to be going over the explanation to this problem because of the level of complexity basically outweighs the necessity to go over how to do this part. So we're just going to go ahead and skip this, and that's that for this presentation.